Today we're going to talk about absolute dating, and that's how we determine the actual age of a rock using the isotopes or atoms inside of it so that we can find out how long ago it formed. And we use some special words in order to study absolute dating, so let's take a look at those. So the words you want to know, isotope's the first one. So when they say isotope, they're usually talking about what will actually be doing the decaying. So it's an atom with a different number of neutrons than some of the other atoms of the same element. Radioactive just means that it's able to decay to something else. So decay, just like animals decay or break down, you're going to break down and make it into a new element sometimes, or a new isotope, that's going to be something different than what it was when it started. So it starts as a parent isotope and it decays to the daughter isotope, so what it's going to be after it decays. The half-life is the time it takes for half of those radioactive atoms to decay to the daughter. So we're going to look at that in just a second, but one to keep in mind is carbon-14. Now, carbon-14 is an isotope of carbon that's used to determine the age of organic material, like living things. We especially like that for using things in the recent time periods, especially humans or ancient humanoids. We would use carbon-14 because it has a short half-life of 5,700 years. Most half-lives of some of our other ones that we'll talk about are much, much longer, or millions of years. So you would use that for rocks, millions of years for rocks, and organic things tend to be carbon-14 for the short half-life. So now let's take a look at what we did with the M&M lab. So if you remember on the M&M, radioactive M&M lab, what we did was we looked at M&Ms and we pretended that some of them were, that 100 of them were radioactive. And then we would shake the M&Ms for 713 million years, which was our half-life that we made, and then see how many of them were still radioactive when we dumped them out. Now, I have made a curve that would be on a perfect scenario. So if it were a perfect world, after one half-life, 50 of the M&Ms would have decayed. So if we look here, here's my number of decaying, or number of radioactive M&Ms rather. So if I look at 50, I plot my point at 50 after one half-life, which is 713 million years. So let me go ahead and write that in there, that one half-life, sorry for the camera pause, my bad. Ooh, sorry guys. So after one half-life, that's 713 million years. Two half-lives is 1426, because every half-life is the same amount of time. It's always 713 million years. So every half-life, so on my chart here, I actually am showing 5 half-lives. Now, many of you had more than 5 half-lives, so it kind of depends on your actual element that you're looking at. But for our M&Ms, I'm looking at 5 half-lives here, and each time I look at it, half of my atoms are going to decay. So I start at the very top up here, all the way up with 100 atoms that are radioactive. After one half-life, I drop down to 50. After a second half-life, I'm all the way down to 25% because I've lost another half. So I had 50 and half of 50 is 25. Then another half-life, so half of 25 is now 12.5. So now I've gotten down another half. So then we're going to go down to 6.25 for my fourth half-life. And we would continue to do this until we got very, very, very close to zero, and eventually maybe zero. But this is an exponential curve, so it's decaying each time you have half of your atoms decaying. That's the half-life. And our half-life for M&Ms was 713 million years, which is very similar to uranium-235.